G'day Internet, my name is Andrew Russell and I'm the lead engine developer on River City Ransom Underground. No video today, just the slides. Today I'm going to be going into an in-depth discussion of the networking in River City Ransom. To do that, let's start by looking at how a non-networked game works. So let's say this box represents the current state of the game world. Let's say we're on frame number n, and if we apply some input to that game state, we're going to get frame n+1. And then the next frame will be n+2 and so on. This is how a normal single-player game works, or a game with local multiplayer. But we want to support online multiplayer, so we need to do something a bit more sophisticated. What we need to do is root it in something called functional programming. So in regular programming, if you've got some state, you can just go in and modify that state directly. So let's say I want to move a character's position. I just go in and set, character.position.x equals whatever and so on. And it directly changes that in the game state. Whereas in functional programming, all of the state is read-only. So to advance time, you apply a function to the game state on frame n, and you get a completely different state that represents frame n+1. So expressed as a mathematical notation, it would look something like this. In fact, it would look something like this because we need to take into account the player's input. The important point is that we get to keep both copies of the game state around as well as the input. What we can do then is keep applying this process to create new states as time advances. And then the final state that we get is what we're going to display on the screen. Now the issue with purely functional programming like this is that it can be very awkward to program this way, especially for typical gameplay code. We'd much rather write our gameplay code in the conventional style, where we just write directly into the game state. So if you watch the previous episode of the DevLog, you might see where this is going. So we've got a serializer and what we've called a rollback driver sitting underneath the game state, and we use those to basically cheat. Instead of writing our code in a functional style and dealing with all the issues that creates, we simply serialize the game state after each frame, along with the input used to create that state, and then the rollback driver keeps track of it all for us. And this gives us the same data that we would have had we been programming in a functional style without all of the fuss. But Andrew, you might ask, what does this have to do with the networking? Well, that's a good question. When you're doing functional programming, no matter how many times you apply the update function, if you give it exactly the same inputs, you're always going to get exactly the same output, even if the function is running on two completely separate computers. So let me give you an example. So let's say we have two computers connected on a network, and one of those computers starts up a game and gets an initial game state, and it sends a copy of that game state over to the other computer. Now the size of this state snapshot is too large to send every single frame, but doing it once at startup is okay. Now, as an aside, there are many games that do send snapshots every single frame, including my other game Stick Ninjas and most first-person shooters. They'll do something like this, but they have to do a great deal of trickery to reduce the amount of bandwidth that this uses. And obviously this won't work in a peer-to-peer networking situation like we're using on River City. So let's go back to our example with our two computers. And both of those computers have a starting point now. And if we start applying inputs and advancing the game state, you'll see that the simulations start to diverge because our update function is being given different inputs. So what we need to do is we send the game inputs across the network. The result is that both simulations end up with exactly the same game state after each step. And this will work for any number of computers on the network, as long as they're all sharing their inputs with each other. So let's simplify our diagram now back down to a single computer. This time we've got local input, and we've also got input coming down from the network. But there's a big problem with this diagram, and that is all of the input coming down from the network will have associated latency. That is, the input for any remote player won't arrive in time to simulate the frame that it's associated with. So basically we have to guess what those inputs are going to be. But what if we guess wrong? The simulations will diverge because we're using different inputs. So the solution to this problem involves leveraging functional programming again, and the fact that we've been keeping a buffer of the previous input and game states. So let's say these are our buffers. We've got our input buffer and we've got a game state buffer. And as you can see, many of the later inputs in the input buffer are unknown because they haven't arrived yet. We've had to guess what those will be. Now let's say a new input arrives from the network, and if it were the same input that we guessed originally, we could just ignore it. But let's say it's different to the input that we guessed. This means that all of the states that we calculated from that frame onwards were calculated incorrectly. So this is okay because the rollback driver has been keeping a copy of that game state. So what we can do is we can just go back and recalculate them all. So this is where the rollback driver gets its name, because we're rolling back the game state to the last known valid state and recalculating from that point. At the end of this process, we have an updated set of buffers, and the final frame in that buffer is what gets displayed to the user. And if we follow this exact same process on every single computer on the network, they all end up simulating exactly the same thing, even if they have to go back and correct themselves a few times. So hopefully this video has given you a good idea of the core algorithm underlying our network system. There's a lot more detail involved to make sure players can join and leave in the middle of games and so on and so forth, but that's all I have time to go into for now. So thank you very much for watching, and I will see you next time.